Hi, and welcome back to Find, Solve, Explain. Today I'm going to go over BMO2 2020 question 4. This one involves a number of fairly complicated ideas, but has quite a nice solution. First of all, a sequence b1, b2, b3 of non-zero real numbers has the property that bn plus 2 is equal to bn plus 1 squared minus 1 over bn for all positive integers n. Suppose that b1 is equal to 1 and b2 is equal to k, where 1 is less than k is less than 2. Show that there is some constant b depending on k, such that minus b is greater than or equal to bn, which is greater than or equal to b, for all n. Also show that for some 1 less than k, for some k, effectively, there is a value of n such that bn is greater than 2020. So initial things to realize: 2020 fairly obviously won't matter. The number doesn't have any properties that seem to relate to the question, although this could be wrong. Second of all, we can start by taking a look at this equation. Timesing both sides by bn, we get that bn plus 2 is equal to bn plus 1 squared minus 1. The key part to realize is that this is independent of the value of n. In other words, if we rearrange this briefly, and then this is clearly equal to, by replacing bn plus 1 with bn, because of the independence. So, now we have two equations, both of which are equal to 1, and are therefore equal to each other. We can then rearrange them to get, plus 1. We can then rearrange them to get bn plus 1 bn plus 1 times bn minus 1 plus bn plus 1 is equal to bn times bn plus 2 plus bn. And this means that bn minus 1 plus bn plus 1 all over bn is constant, as it is equal to bn plus 2 over bn plus 1, just from rearranging. Now, if we take the initial conditions, that being b1 equals 1 and b2 equals k, by setting bn to be equal to, or by setting bn to be equal to 1, first of all we just have to work out b3, which is fairly simple, as it's just 1 over k squared minus 1, which is equal to k squared minus 1. Now we can apply the formula that we learned, which gives us that 1 plus k squared minus 1 over k is equal to some constant. Thankfully, this constant is just k. This makes our life much easier. So, now we know that there's this common term. We can expand out the sequence once again. We can expand out this expression once again. This is a recurrence relation of order 2. Now, by taking a look at its characteristic polynomial, I'll call the solutions t. We can see that so the solutions will be of the form of these to the n times by some other constants determined by the initial conditions. So the solutions to this, simply using the quadratic formula, are k plus or minus the square root of k squared minus 4 all over 2. However, the really interesting part about this is that we know that k is between 1 and 2, which means that k squared minus 4 is always negative. In other words, this number is complex, as the square root of a negative number is not real. As it is a complex number, we can represent it in the form a times e to the I theta. In this case, a is relatively easy to determine, as k over 2 squared minus, as it's negative, the square root, minus k squared minus 4 over 2 over 4, so we're squaring it, is just equal to 1. So a therefore has to be equal to 1, as that's the modulus of the function. So this gives us, this is actually a complex number. However, before we complete this, we're going to have to find solutions. So we're going to call these two roots, one is the plus and one is the minus. How about t1 and t2, and we're going to call the constants we're multiplying them by big A and big B. So big A times t1, which is the positive one, plus big B times t2 to the n is equal to bn. So by taking n equals, or we can just edit it to make this work. By taking n equals 0, or by taking n equals 1, we get b1, which we know is 1, is equal to a plus b. And then we can also expand out this for the second term, which is when with the full expanded form of these, just the 1. And this gives us that a times by t1 plus b times by t2 is equal to k. And of course, a plus b equals 1. And the first part of t1 and t2 is the same, k over 2. So we have really k over 2 plus the complex part of a minus b, as one of them has a minus. Which is therefore equal to k over 2. From this and careful application of the first principle of a plus b equals 1, you are actually able to get formulas for a and b. And when you use the fact that this is a complex number and can be written in the form e to the I theta, which is also equal to cos theta plus I sine theta, it becomes clear with it being fairly obvious that k over 2 is equal to cos theta, as this is the real part, and the square root of this would be just for the positive. For the negative, you replace the plus with a minus. It turns out when you rearrange these, you actually get b, I believe, being equal to the square root of k squared minus 4 over 2k. And substituting these in, this is actually equal to 1 over 2I tan theta. Plus a half. The half is to make these work, and for a and b, this would be a plus and minus. So, now that we have those solutions, we are able to plug it back into the full equation using the trigonometric substitutions, and get that from, where is it? Yeah, from here, we're able to get that b of n is equal to a fairly simple, so first of all, when you raise this to the n, 1 to the n is still 1, and this just becomes I n theta, so we can put n's in here. Important concept to note. This will actually go to so in reality, for the real part, first of all of the signs cancel because we're dealing with plus and minus for a and b, giving us just cos theta, cos n minus 1 theta plus, now using the plus and minus tan with the signs and the i's cancel, to give us sine n theta over tan theta. This will obviously, so if tan theta is incredibly small, the maximum of this entire thing will be 1. Well, there is a bound on this thing, as this is always less than 1, and this will be less than 1 over tan theta. Theta remains constant throughout all of this. So this sets a bound, and this can also be larger than which is equal to b. And this will also, in certain cases of theta, because of 1 over tan theta, if tan theta is incredibly small, can be greater than 2020. And so we are done.